So continued from here, my in further reduces to in equals, and this in also brought to the left will reduce this to in plus n minus 1 times in, which comes to the left, and the right hand side is minus sine power n minus 1x cos x, and this is plus n minus 1 in minus 2. So this, on simplification, gives 1 plus n minus 1 of in when I take common, and this is equals minus sine cos x is what we get. This gets cancelled and I get n times in is this of cos x of this. Therefore, in is minus sine power n minus 1x cos x by n is how the reduction formula is obtained for integral sine power nx dx is minus sine power n minus 1x cos x by n plus n minus 1 by n in minus 2. Now let's take the odd and even cases of the reduction formula for integral sine power nx dx. Now, as we know that the reduction formula for in, that is integral sine power nx dx, is given by the formula minus sine power n minus 1x cos x by n plus n minus 1 by n of in minus 2, then the biggest question is what would be the last term until the reduction. So here come the two cases. One is when n is even and when is odd. So for this, if n is even and n is odd, then interestingly we see that if n is even, this reduces to I0. Implies the last reduction is I0. And if n is odd, then it reduces in the form 7, 5, 3, 1. So here the last reduction is I1. So here the last reduction is I0, and in this case of n odd, the last reduction is I1. Therefore, let's calculate I0 and I1 in this case. Now, in is integral sine power nx dx. I0 is when n is 0. Therefore, simply substitute n equal to 0 in this formula. And sine power 0 is 1. So, 1 dx is x. That implies I0 is x. When n is even, the last reduction I0 is substituted with x, and here my I1 is when n is 1, and therefore sine power 1x dx, which is minus cos x. Therefore I1 is minus cos x, which we're going to substitute in case of n being odd. Therefore, if the value of n is even, my last reduction I0 is x, and if n is odd, then my last reduction, which is I1, is minus cos x, as we substitute here. Now let's see the significance of reduction formula for this, and of course this helps in evaluating integrals of this types for considerably larger values of n, or for any value of n being an integer. Suppose I have a problem which says integrate sine power 4x dx, then clearly this is identified as I4 with n equals 4. Now, as we know that the value of in is given by minus sine power n minus 1x cos x by n plus n minus 1 by n of in minus 2 as the reduction formula for sine power nx, taking n equal to 4, I get my I4, which is reduced to minus sine power 4 minus 1x cos x by 4 plus 4 minus 1 by 4 of this by substituting n equal to 4 in the reduction formula. Now this would be by 4 plus 3 by 4 of I2 which is nothing but of I2 where n is 2. So to find I2, this reduces to minus sine 2 minus 1x cos x by 2 plus 2 minus 1 by 2 of this by substituting n equal to 2 in case of this being equal to this. Now this would be by 2 minus sine cube x cos x by 4 plus 3 by 4 of by 2 of I0 is what we get. Therefore, I4 of this will be minus by taking expansion of the brackets sin x cos x plus 3 by 8 of I0, which is x, because we have found that I0 is the last reduction if n is odd, and then I get I0 is x. When n is even, I get I0, which is x. Is how we simplify integral of sine power nx using the reduction formula in, and then the answer for integral sine power 4x is minus sine cube x cos x by 4 minus 3 by 8 sin x cos x plus 3x by 8 plus the constant of integration c. Reduction formulae connected with integration. Now let's see the reduction formula for integration of the type sine power mx cos power nx dx, where m belongs to z plus the positive integers and n belongs to z and n is always greater than or equal to 2. So are the conditions through which we are going to integrate sine power mx cos power nx dx. Generally, integral of sine power mx cos power nx is denoted by imn. Now imn is integral which on reduction through integration by parts leads to the answer as 1 by m plus n cos power n minus 1x sine power m plus 1x plus n minus 1 by m plus n im n minus 2 is how we get the reduction formula for Imn integral sine power mx cos power nx dx as the formula 1 by m plus n cos power n minus 1x sine power m plus 1x plus n minus 1 by m plus n Im n minus 2 is how we get the reduction formula. Therefore, as if suppose I wanted to find the integral of I32, that is integral sine cube x cos square x dx, then I assume my m is 3 and my n is 2 and then use the reduction formula, which in the next stage reduces to I32 reduces to I30 where n is 0 and then finally the whole of reduces to Im, and then I can use this with connected with the previous session of Im, which is I30 is Im, that is I3, which is calculated using integral of sine cube x dx as done in the previous session. So In is calculated and then the whole answer is obtained for I32 in each of the case. So reduction of n is connected with m in the whole problem in this manner. Say for example, I take I32 connected with this. Now let's see the reduction formula for tan. So if I would like to evaluate integral of tan power nx dx, where n is an integer and n is greater than or equal to 2, then we use the similar reduction formula, assuming In equals integral tan power nx dx. This reduces to the form tan power n minus 1 by n minus 1 of this, where I have two cases for this, the odd and even case, n even and n odd. Then if n is even, my last reduction reduces to I naught because 6, 4, 2, 0, etc. And this will be integral of tan power 0x dx, which is x. I get I naught is this. And here the last reduction will be I1, which is integral tan x, which is log mod secant x plus c. So integral of tan x is log mod secant x, which is I1, and this is I naught. So if n is even, the last reduction is x. If n is odd, the last reduction is log mod secant x plus c, which we use accordingly with n. Now next is the reduction formula for integral secant power nx dx for n belonging to z and n greater than or equal to 2. So as in case of integral tan power x, similarly I take my integral secant power nx dx as In and then expand this using the reduction formula, and I get this to be 1 by n minus 1 secant n minus 1 n minus 2 tan x plus n minus 2 by n minus 1 of I is what we get in integrating this equal to this. So the reduction formula for secant power nx is this, which we get. Now let's see the last reduction for n even and n odd. Let me take two cases where n is even and n is odd. Clearly we know that if n is even, it reduces in the form 8, 6, 4, 2, 0. So my last reduction is I naught, which is nothing but secant power 0x dx, that is x, because this reduces to integral dx. And when n is odd, my last reduction is I1, which is secant power 1x dx, where integral secant x is log mod secant x plus tan x plus c. So for n even, the last reduction for integral secant power nx dx is x, and for n odd, my last reduction for this is log mod secant x plus tan x plus c. Is how we understand the last reductions with the two cases n even and n odd. If suppose I have integrals of the form integral e power x times f of x plus f dash x dx, then we have an exclusive formula for integrals of this type. So let's see the derived formula for integral e power x times f of x plus f dash x dx. So integral of e power x times f of x plus f dash x dx is directly given to be e power x f of x plus c. This will be directly multiplied with this, is what we get as the formula in case of this integral. So whenever we find an integral of the form e power x times f of x plus f dash x dx, if you can express these two terms inside the bracket as derivative of each other, then directly I can obtain the answer as e power x to that of the function, is what we get here. So let's see some example problems connected with this formula. So for example, I have to evaluate integral of e power x times x plus 2 by x plus 3 whole square dx. Now let's see if I can use this exclusive formula in integrating this when this is converted into the form f of x plus f dash x. So let's try to split the terms out here. Now as I see here, I can further modify this function by taking x plus 2 written as x plus 3 minus 1, because 2 is written as 3 minus 1. Now the idea behind writing 2 as 3 minus 1 is to make these two to be similar, so that I can split and I get the simplification done easier out here. So this can be split as x plus 3 by x plus 3 whole square minus 1 by x plus 3 whole square. So this is split as this by this minus 1 by this dx. So the function gets split into x plus 3 by x plus 3 whole square minus 1 by x plus 3 whole square. Now clearly I see that 1 of x plus 3 gets cancelled, and this reduces to the form integral e power x of 1 by x plus 3 minus 1 by x plus 3 whole square of dx. So this is the final representation where I get this. Say I take this as function f of x. Let's see if the other term gets to be f dash x. Now clearly I see that f of x equals 1 by x plus 3 implies f dash x is minus 1 by x plus 3 whole square, as using the derivative formula leads to this, which is nothing but this, as written as minus 1 by this. So if this is f of x, this is f dash x. Now clearly I observe that this is in the form of e power x times f of x plus f dash x, which is given by the formula e power x f of x plus c. Therefore, integration of e power x times x plus 2 by x plus 3 whole square dx, which is the given problem, is nothing but e power x by x plus 3 plus c. Integration of the form e power x f of x plus f dash x dx is used to integrate this to be equal to this.